presentation of this yet, please do that because they will give you after him. And then there are some suggestions of places where to meet lunch on the blackboard which is in the corridor. And the last thing is that, okay, tomorrow evening we will have a social dinner. Since we have to book a place, we will ask in the afternoon who is coming, so start to think about whether you want to join us or not. And so it's my pleasure to introduce Gavril Farkas, who is speaking about modular spaces of all the theta characteristics.
Yes, thank you very much for the invitation. So I will discuss, I think I can close this. I will discuss about a series of joint papers with Sandro Verra. And they concern the kind of a complete birational classification that we achieved on the moduli space of spin curves. And this is a story in several parts, and some of you probably heard me talk about other parts of this story. And so the moduli space in question is the moduli space of spin curves, which will be denoted by SG, and it is the parameter spaces for theta characteristics on curves of genus G. Yeah, so theta is a theta characteristic. And as you probably know, theta characteristics have a deformation invariant, which is the parity. And so you look at the number of sections, modulo 2, and this stays constant into in deformations. And accordingly, this space has two connected components, SG plus and SG minus. Yeah? So this is the even and the odd spin moduli space. And well, so these numbers of even and odd theta characteristics are constant over all curves of genus G. And I should just say that the number of even theta characteristics is 2 to the G minus 1 times 2 to the G plus 1. And the number of odd theta characteristics is 2 to the G minus 1 times 2 to the G minus 1. Yeah? So these were things which were sort of known to the Germans who did theta functions in the late 19th century, and they were sort of brought back to modern mathematics and algebraic geometry in particular by Atiyah and Mumford. Okay, so these are these moduli spaces. So there are, of course, now when I talk about the spin moduli space, there are two moduli spaces in question, the odd and the even spin moduli space, and they admit the linear Mumford compactification, which I will discuss very briefly because that's not the main point of my talk. So here there is an étal, finite étal morphism of stacks from the spin moduli space to MG. So here you can put plus or minus as you wish. And MG has compactification by stable curves, the linear Mumford compactification. And there is a way, a very nice way of closing this diagram and having here a finite ramified branched cover. This time is no longer étal even at the level of stacks. It's a branch cover, and this is the moduli space of stable spin curves. So this was initially constructed by Kornalba, but now it can be also defined in the kind of larger context of Abramovich-Istoli. It doesn't matter. So there is a very good compactification. I mean, as good as the moduli space of stable curves of genus G. And the question is, what can we say about this moduli space, right? So this is the object that we want to study, right? So maybe I should make a comment. Yeah. So this space appears a lot in nowadays in kind of string theory. There is a lot of actually wrote several papers, and then of course lots of people follow this. And that paper that is interesting for string theory is that space that is interesting for string theory is SG plus, the even spin space. It's exceedingly interesting. As far as I know, SG minus is of no interest to string theory, but nevertheless, we allowed ourselves to study it. And we treated both spaces on equal footing, so to say. So the results that I will talk about are the following. Actually, not all of them. So there are two theorems. The first one concerns SG+. So that SG+, the odd spin, the even spin moduli space is a variety of general type for G greater than or equal to 9. It is a unirational variety for G up to 7, and it is a Calabi-Yau variety for genus 8. In particular, it has, I mean, in the right setting, in part, that is certainly the Kodaira dimension of this is 0, and we can actually prove a stronger statement than this, right? So S8 plus is not what we call the Calabi-Yau variety, because the canonical class is not 0, but there is a model, a Mukai model of S8 plus, which really becomes a variety with a trivial canonical class. So about this I talked a fair number of times, and this is kind of a nice story. So these unirational models here, this was kind of done by constructing kind of sort of, we call them Nikulin models of kind of of theta characteristics. So these are kind of special K-free surfaces endowed with an involution. And so it's more than just, you know, we kind of tell you what the moduli space here is. And of course, this is very, very exotic case, because it's the first time that you have a Calabi-Yau moduli space appearing in nature. But this is not what I want to talk about. I want to talk about the corresponding story for SG minus. So the theorem here is the following. So this is theorem 2, also with Verra, that this time we look at SG minus. So this is a variety, this time of general type, for genus greater than or equal to 12. And it is a uni-ruled variety, so negative Kodaira dimension in particular, for genus up to 11. So there is at least a full classification by Kodaira dimension, and we have actually more precise results. In fact, here it's unirational for G less than or equal to 8. And it is rationally connected for 9 and 10. And it is uni-ruled, but not unirational for genus 11. So that's the situation.
Can you remind us what happens to mg bars?
Yeah. So for mg bar, it's yeah. So mg bar is has negative Kodaira. It's a uni-ruled for G up to 16, and of general type for 24 or higher and 22. And there are some partial results for 23, and nobody has any idea what is in between. There is no convincing. I said nobody has any idea, so we might as well get Calabi-Yau. Yeah. But I don't see any, yeah, we don't know. Yeah. And then there is no, of course, the point is that, yeah, so I should say something. So here there is a complete classification, right? And the reason we can achieve a complete classification here and not here is that this change happens much earlier. I mean, below actually genus 11. And when you see this range, of course, then you immediately, well, should perhaps think of K-free surfaces, yeah? I mean, and of course, we have a much better understanding of curves of genus 11 or less than 11 than curves of genus 17. Yeah, so this increase in genus is almost exponential as you go, you know, from 11 to 12 already is, maybe exponential is too much to say, but it's a significant increase in complexity. Yeah. So I won't say anything about that. I will say, so I will talk about this. And okay, so the point here, so the story here has two parts which are largely distinct, and there is this general type story which I will discuss very briefly. And most of the talk I would like to discuss this title of the story. Actually, we kind of determine what this moduli space is. I mean, in terms of the corresponding Mukai variety. So it's not just, there is unirational parameterization. We tell you what the structure of the moduli space is. But let me just get on with so the general typeness result, first of all. And I should say a couple of things about this compactification. At least very briefly. And instead of defining what the points in this moduli space are, I mean, that's not such a illuminating exercise, perhaps. I should just, so I said that we have now, so from now on, I will only talk about the odd, yeah, so I should have said, what is an odd theta characteristic? Yeah, perhaps this would have been a good comment to make at the very beginning, yeah? So an odd theta characteristic is simply, so you take a curve, yeah, you embed it in the canonically, and an odd theta characteristic is just a bunch of points, yeah? So then usually it will have only one section, so it's a g minus 1 points, which are everywhere tangent to the canonical curve, yeah? So they span a pg minus 2, and this pg minus 2 intersects the canonical curve everywhere twice, yeah? So this is everywhere tangent plane, hyperplane. So you can also view it in terms of projective geometry. You can also view it in terms of theta functions. And this is how it was traditionally viewed. So this is what we are talking about. OK, so what is this minimum for compactification? So we have this. So I mean, I said we have such a map. And it's a finite map. And let me just discuss the branching of this map, right? So the branching I would like to briefly discuss, because this plays an important role. It makes you actually understand the difference between the moduli space of curves and the moduli space of spin variety of spin curves. So the branching is that, so mg has a divisor delta 0. So this is the locus of irreducible curves with one node and their degeneration. Yeah? So you take a closure here. So this is the boundary divisor. So this is a curve of genus g minus 1 where I identify 2 points. And then, so let me just, so what are the spin curves on such a curve? This is a simple exercise. You look at a normalization map. So this is the normalization map. So and here are the points P and Q are still separate points. And then, of course, a spin structure. So on the nodal curve, it can, well, you look at degenerations of bundles of degree g minus 1, whose square is the canonical bundle, right? So the canonical bundle will translate into the dualizing sheaf of this nodal curve. And now you have two possibilities, whether on the nodal curve this spin structure is locally free or not, right? And according to this, you will have two components for the pullback of the boundary divisor delta 0. So there are two possibilities here. The first possibility is that, so I look at when you have a locally free spin structure, and then I look at, so elements of this type, n, p, q. So this is an element, it's a curve of genus g minus 1. So the genus of n is, of course, n minus 1, g minus 1. So pointed curves of, two pointed curves of genus g minus 1 plus, okay, so if I want to have a locally free bundle on the nodal curve, this should be a bundle of degree g minus 1 on the curve of, on n. And then I have here a bundle n, which is a root of the canonical bundle of n twisted by p plus q. You see that at least the degree matches. And then, of course, to give a bundle on the nodal curve, I have to give also a recipe for gluing the fibers, yeah? Plus the unique gluing of the fibers at Q, such that H0 of C and theta is odd. Yeah. So that's that, and this forms a boundary divisor, and this is called alpha 0. So, I mean, yeah. So this is now okay. You have to prove something, but fortunately, Kornalba did this for us. That actually you can do this in families. Yeah. That you can find this gluing systematically. And then modulo that, this boundary divisor corresponds just to, you know, two pointed curves of genus 1 less, together with the root of this bundle. Yeah. And then, of course, there is a second situation when you actually, so this was for this, this corresponded to the case when you had locally free shifts on the nodal curve. And now you look at the case when you have non-locally free shifts, and this will be the divisor called beta 0. And then in this case, you have to sort of blow up, if one may use this terminology, n, the node, and you insert a P1, and you have here P and Q 2 points. Yeah, so this is now a semi-stable curve. And then, so elements here are kind of, unions like this. Yeah. And now you have, okay, so now you will have to provide a line bundle on this. So it will be a non-locally free sheaf on the nodal curve, which will correspond to a locally free sheaf on this semi-stable curve. And here you are going to put O of 1 on the P1. And here you are going to put an odd theta characteristic. Right, so let me just say like this. So theta restricted to P1 is OP1 of 1, and theta restricted to n is a root. It's a theta characteristic which is odd. So these are again. So this is another boundary divisor. So right, if you wish, these are just two-pointed curves of genus G-1 together with the choice of an odd theta characteristic. Yeah, and you have an entirely analogous story for the even space, where you just replace the word odd by even systematically. Yeah. And now the point is that it turns out that the pullback of the boundary divisor delta 0 is equal to alpha 0 plus 2 times beta 0, which is to say that this beta 0 is the ramification divisor of this map. Yeah? I mean, I'm not proving this, but you can convince yourself that it is at least plausible, because you can, you should get, when you see how many such, what is the degree of this over delta 0, the degree of alpha 0 over beta over delta 0, and the degree of beta 0 over delta 0, you add them, and you should get the number of odd theta characteristics on a smooth Riemann surface of genus G. Yeah. And then, of course, then there is a kind of, it's really easy to show that there is no further ramification, there is no ramification over the other boundary divisors, so I will ignore them from the rest of the story. Okay. So then we have determined the ramification of this map, and then, of course, it's very easy to determine the canonical class. And by the Hurwitz formula, the canonical class of SG is simply the canonical class, the pullback of the canonical class of MG, plus the ramification divisor. And this has been determined by Harris and Mumford, and this is 13 lambda minus 2 delta 0 minus other boundaries, which don't play much overall. And then you get that this is 13 lambda minus 3, no, what is it? Yeah, minus 2 alpha 0, oh, okay. 0 minus 3 beta 0. Yeah, so this is how the canonical class looks like, right? Because I use that formula here. Okay, so that's just a question whether this, or what sort of class is this? Is this positive, negative? Yeah, so that's the question. Okay, and then, well, the way of proving that something is of general type is just to construct an effective divisor which has better class than this. And these divisors, so kind of effective divisors on SG minus. So now there is a discussion, what is the best divisor on the spin space? So on the even spin space, there is a God-given divisor. I mean, you can ignore it, but it would be not advisable to ignore it. And actually, that's what we used to prove that theorem there for genus greater than 9. This was the theta null divisor. So here on SG minus, you have to think a little bit. But there is still, there is not maybe such a canonical choice, but there is a choice which is fairly simple to think of. So an odd theta characteristic is just G minus 1 points, right, which form an everywhere tangent hyperplane. And you simply ask that these G minus 1 points form a non-reduced scheme. So 2 points come together. Yeah, and this is certainly going to be a divisor on the spin space, right? So we look here at kind of degenerate theta characteristic, I can say like this. And the divisor that we have is, I mean, we did other experiments, and this was anyway the best, and it has a pretty good, simple description, C theta in SG minus, such that the support, yeah, so generically, this will have only one section. It's odd, right? It won't have three sections, that is higher codimension. So I can talk about the support of the theta characteristic. It's just a collection of G minus points, G minus 1 points. Is non-reduced. Well, I suppose the support is by definition non-reduced. So what do I want to say? I want to say that the divisor is non-reduced, yeah? Yeah. And this is an effective divisor, right? So it's of this type. 2x1 plus x2 plus xg minus 2. And then this is a divisor, as I said. And we sort of computed this class of this divisor on the compactification. So with Verra, we computed that if you take the compactification of this divisor, you take the closure, you get this class. It's G plus 8 times the Hodge class, which is just the pullback of the Hodge class from Mg, minus G plus 2 over 4 alpha 0 minus 2 beta 0 minus highest or higher order boundaries. Higher order boundaries. Yeah. So we proved this with algebrogeometric methods, and then later Zograf and Kokotkin found another proof of this formula with kind of Bergman kernel methods, and reassuringly the two results are the same. So this is a class, right? So and then you see that, of course, you compare this to the canonical class, you'll see that this will not be enough to make the canonical class positive, because simply this coefficient of beta 0 is too small. So you see that the slope of lambda over alpha 0 is what is about 4, right? That's certainly less than 13 over 2. That's fine. That's very good. But this coefficient is too small. So you have to compensate, right, this lack of negativity on the beta 0 side by pulling something back from Mg. And but of course, we have a lot of knowledge about divisors on Mg. And we can use this. And we have the Brill-Noether divisor. So pi was this forgetful map from Sg minus to Mg. And you can pull back the Brill-Noether class. This is just a class of, curves which have a linear system of rho equals Brill-Noether number -1. And this is a formula which is well known due to Harris and Eisenbach, G plus 3 lambda. So this part of the talk is fairly standard, I must say. G plus 1 divided by 6, and here is alpha 0 plus 2 beta 0. So this class is also effective. Yeah? And now you can do linear algebra. And you can use these two classes and to get something that looks like the canonical class. And what I am going to do is I will, maybe. Well, I suppose. Let's see. Let's use this. No, it's not. The coefficients, you mean? Yeah, that's a good point. Of course, you have to control the others. But things work in your favor, actually. So, yeah, I know the other form. I know the other coefficients. I just didn't write them down. Yeah, and in fact, it always comes to these coefficients over delta 0. But of course, you need to have an argument for that. So for the canonical side, and actually for all the free divisors, I know all the boundary coefficients. And sometimes for other divisors, we don't know all the boundary coefficients, but then we have bounds on them. So I don't know. Okay. So you can simply compare these formulas, and then I will make the following. I can make a linear combination of these divisors, and I will get something. That, so I take 2 to the 2 divided by g minus 2. So I just make a linear combination. You'll see what is the point of this. This is dg plus 3g minus 10 divided by g minus 2 of the pullback of the Brill-Noether divisor. So if I write it in this way, then I will get, then I will get it in a form which is compatible with the canonical form. And this is kind of 11g plus 37 divided by g plus 1 lambda minus 2 alpha 0 minus 3 beta 0 minus higher order boundaries, yeah? So that was the point of choosing these bizarre coefficients, because I wanted to make it like, to get a vanishing of order 2 respectively 3 at infinity, just like in the formula for the canonical class. And now you have to believe me that this vanishing here is worse than the vanishing of in the canonical class there. Actually, the vanishing in the canonical class is either 2 or 3 throughout the boundary. Yeah? So this is an effective class which we construct. And then, of course, now you can compare this to 13, to the slope of the canonical class. Yeah? And then you see when this inequality is satisfied, which is satisfied for g greater than or equal to 12, I believe, hopefully. Yeah? Then, of course, it follows that Sg minus is of general type, which is what we claim, provided that what we did is correct, provided that there is a Brill-Noether divisor, if there is a Brill-Noether divisor. I mean, a Brill-Noether divisor, that's an arithmetic condition. This happens only if g plus 1 is composite. So 12 plus 1 is 13, that's prime. That's not composite. There is no Brill-Noether divisor on M12. So this argument actually will work, in fact, only for g greater than 13. I mean, you can now complain about 16, but there you have, when g plus 1 is 17, again, prime, but there you have something. There are many other ways of solving this problem. But so anyway, this is the argument for g greater than 13. And then the case g equals 12 is very hard. So this case g equals 12, it takes about as much as all the other cases for some reason. This is very resistant. Of course, you would like to have the result, but then what I said here, you can still be used. And you have that S12 minus is of general type, provided one can construct, exists an effective divisor on M12 of slope. So you see for 12 here you have equality. Yeah? So you have equality here for g equals 12. Of slope less than the slope of the this slope of the Brill-Noether divisor, which doesn't, I mean the slope of the slope of that class, or slope less than 6 plus 12 over g plus 1. So this is very difficult to construct such divisors because, in fact, one knows that such divisors, if they exist, they have to contain the locus of curves on k-free surfaces. Anyway, so that's the challenge, and well, there is such a divisor. And there is such a divisor, and this is, what is this divisor? So I can just sort of describe this to you. So I start with a curve of genus 12. Yeah, so there is such a divisor. There is such a divisor. So a curve of genus 12 has a finite number of pencils of degree, a general curve of genus 12, have a finite number of pencils of degree 7. And then you look at the residual, and this is a G515. So there is a finite number of maybe something like 84 ways of embedding a curve of genus 12 in P5 with degree 15. Yeah? So this is O of 1. And now you look at the quadrics containing this curve. So let's look at the quadrics. You compare dimensions here. So here you have, it's in P5, so the quadrics are 7 choose 2. This is 21. And here, this is a non-special linear system. So by Riemann-Roch, this is 31 minus 12. It's 19. So there is a pencil of quadrics containing the canonical curve, right? So there exists, so let's call this map mu, C. So there exists a pencil, a P1, pencil of quadrics containing C. The condition we ask is that this pencil of quadrics be degenerate. So a pencil has one invariant, which is basically, it's a pencil of quadrics in P5. In a pencil of quadrics in P5, there will be 6 quadrics of rank 5, normally. And we ask that these 6 quadrics are not all distinct, right? And this is a kind of a divisor. Let's call it, maybe I should give it another name here. All my divisors are D. It's not such a good strategy. I will call this H, okay? So H12. So this is the locus of curves of genus 12, such that there exists a G515, which is, I call it O of 1, such that this P1, this pencil of quadric, is degenerate. So this construction may look a little bit complicated, but this is really because you want to have this you want to satisfy this condition. This threshold is very high. You want to have a condition which you know that it will fail along the locus, along the codimension 3 locus in M12 of curves lying on a K-free surface. And this is, we know, this is guaranteed to fail because for curves that lie on a K-free surface, you have here a 2-dimensional kernel. I'm sorry, a 3-dimensional kernel. So you have actually not a pencil of quadrics, but a net of quadrics, in fact. And then, of course, in a net of quadrics, there will be, that condition will kind of break down. And now, well, there is some effort to prove that this is, in fact, a divisor. This is not at all obvious, but it is a divisor. And then there is some further effort to compute its slope. And the slope of this divisor, so this is the ratio of the lambda and the delta coefficient, delta 0 coefficient. Well, this is 373 over 54. Yeah? And if we did this correctly, this is less than 6 plus 12 over 13. And this implies that S12 is also of general type. So in passing, I should mention that this divisor also provides a counterexample to this Harris-Morrison conjecture on slope conjecture. I mean, so this conjecture is expected to fail on all genera greater than 11. But I mean, and it was known to fail on an infinite sequence of genera, but in this sequence there were gaps, right? So the point here was that one has to find for this application a counterexample on M12. Okay, so this is a story about general typeness, and now the talk will move in another direction. So I mean, now I would like to, this is what you can do with general type, and in fact it turns out that for all the genera smaller than 12, we will have structure results for the moduli space. Okay. So. Well, this is okay. Okay, so I would like now to discuss what happens for genus up to 11. Yeah? And so kind of, I would say structure theorems, structure results for Sg minus. And this is for g less than 11. Of course, what makes this interesting is that for genus less than or equal to 11 and different from 10, the general curve of genus G lies on a K-free surface. Yeah? This is well-known theorem. Maybe we can attribute it to Mukai. Parts of it were certainly known before. So let me just define what is, so I start with a K-free surface, which is of genus G. So this is embedded in P to the G, right, by the polarization. And then I can define what is, so it's a polarized K-free surface. I can define what is a theta pencil. So I will define, first of all, the following cycle, theta minus of S and H, right? So SH is a polarized K-free surface. So what is a theta pencil? A theta pencil is a codimension 2 plane in PG. Yeah, so this is G to G plus 1, which has the property, right? So it's a pencil, it's a codimension 2 plane, or if you want, it's a pencil of hyperplanes, which intersects the K-free surface everywhere with multiplicity 2 everywhere. So the degree of the K-free surface is 2G minus 2, like the degree of the canonical curve, right, of genus G. And you expect 2G minus 2 distinct points. But I impose the condition that actually this divisor has everywhere, the intersection divisor has everywhere multiplicity 2, the intersection cycle has everywhere multiplicity 2. Okay, so this is the subvariety of the Grassmannian, and this is G to G plus 1, so this has dimension 2G minus 2, and I impose G minus 1 conditions. So this is a G minus 1 dimensional subvariety that they can associate. This is something I can associate to any polarized K-free surface. So this will play an important role in the uniruledness results. And now I can, of course, look at the universal family of such things. Yeah? So I can now define the universal everywhere tangent plane, if you want, of a moduli. So I will call it theta G. So this is the parameter space for elements of type SH. So SH is a polarized K-free surface, together with an everywhere tangent plane, like here. Yeah, so SH is polarized of K-free of genus G, so degree 2G minus 2. And theta is in theta minus of SH. So what's the dimension of this object? Well, the dimension of this object, well, is, as I said, it's 19 for the dimension of the moduli of K-frees. And then I have to add G minus 1. For each individual K-free, I have this variety is G minus 1 dimensional, so it's 18 plus G. So this is some sort of variety over the moduli space of polarized K-free surfaces. And so these are varieties of general type. They are subvarieties of the Grassmannian, these everywhere tangent planes, right? So it's some sort of auxiliary moduli space over the moduli space of K-free surfaces. Okay. Now, the point here is that when you have such a codimension 2 plane in PG, can be viewed as a pencil of hyperplanes, right? And I will get K-free curves, canonical curves, by varying the hyperplanes in this pencil. And this is what I'm going to do now. Yeah. So I will set up now the following correspondence here. So let's call it kind of HG. So the elements here will be polarized K-free surfaces, a codimension 2 plane like this, and now a curve in this, right? So such a lambda, right? So such a lambda is the intersection of 2 hyperplanes in PG. And then, of course, through a codimension 2 plane, there is a pencil of hyperplane sections. And these hyperplane sections will cut the individual K-free surface along canonical curves. Yeah? And these will be the C's here, right? So S, H, and lambda is an element in theta G. And C is a pencil, is a curve in this pencil. Yeah? So this is now this lies over theta G. And over theta g, this is simply a P1 bundle. Yeah? Because once I fixed S, H, and lambda, all I have is the curve in this pencil. It's a P1 bundle, right? So this has dimension 18 plus g. Now this has dimension 19 plus g. Yeah? So 19 plus g appears in this Mukai count, but this is the different 19 plus g than Mukai's 19 plus g. Yeah? So our 19 plus g is 18 plus g plus 1. Yeah? So Q. You will see, but it's not going to work. You will because yeah, it won't. It's not going to work. So the point is now that I can also go to the other. So it's a P1 bundle. I can look at this map phi, and well, so all right. So I can now forget about the K free surface, and I can actually, of course, I could say I'm mapping to mg, but in fact I'm mapping to the spin moduli space, because actually that was the whole point of doing it like this, right? When you have such an element, so S, H, lambda, and C, so you can retain C. But you can also retain the intersection of this codimension 2 plane with the curve, which will be an odd theta characteristic, actually the half of that. Right? So this will be a canonical device which is even, so you can divide by it. And this will be a theta characteristic. This is an odd theta characteristic. OK, so this is the basic diagram for uniruledness. It's a kind of very simple idea. And now you can simply compare dimensions. Yeah? And well, this is 3g minus 3, of course. This is 19 plus g. And this map has no chance of being dominant other than for genus up to 11. And in fact, we can prove that phi is dominant if and only if, well, it's like in the Mukai story. But as I say, it's, well, I mean, of course, it's like the numerology is the same because we do the same numerology. But this 19 plus g is still different than that 19 plus g. So, and g different from 10. The dominance of the map phi is actually very easy to see because you start with a curve, right? So this is just a bunch of points in SG minus, a general point. In this range, there is a K-free surface that contains the curve. Yeah? And now we simply look. Lambda, in this case, is just the PG minus 2 spanned by these points. PG minus 2 spanned by these G minus 1 points. This is G minus 1 here. And then simply I look at the pencil of curves on the K-free surface that contain these. I'm sorry, I look at the pencil, yeah, that contain lambda through these points, right? So then there is a pencil of hyperplanes through lambda. And that actually gives me the dominance of the map. OK, so actually, so now, of course, this is a variety of general type. Although I must say that we haven't done a study of singularities of this variety. But it has a positive canonical class. Let's say it like this. And this is a P1 bundle over it. So this whole thing is uniruled. So when this map is dominant, then SG minus is also uniruled. And then genus 10, of course, we deal somehow with it. We deal with it because we view it as a boundary of genus 11. I mean, there is a fairly standard trick to also get genus 10 out of this. Yes, and in fact, for genus 11, this map is an isomorphism. Phi is an isomorphism for birational isomorphism for genus 11. So for genus 11, in fact, S11 is a P1 bundle. It's basically P1 birational isomorphic to P1. It's a Zariski locally trivial fibration over this variety of general type. So this is the structure. Yeah. So the moduli space of Spinkers of genus 11 has this structure. It's P1 times the moduli, this universal everywhere tangent plane over the moduli space of K-free surfaces. So this is a kind of accidentally, it's a sort of accidentally. It's not it's uniruled because it has this P1 bundle structure, but not more. Okay. So that's the situation with uniruledness. And now I would like to continue to go down in genus, right, and rather than up. and to describe these Mukai models, I mean, the structure theorems for smaller genus. Okay. All right. So now genus at most 9. And here I have to talk first about Mukai models. This is for the moduli space of curves of genus G. So perhaps many people in this audience know that for G less than or equal to 9, Mukai, in a sequence of very well-known papers, produced a rational homogeneous variety, which I will call it, I wish I could call it MG, but that would not be a good idea. So I will call it VG for variety, yeah? Which is embedded, this is of dimension NG, and it is embedded in P capital NG. These are all Mukai notations, actually. This is NG plus G minus 2, which is Fano, and has a it has index 2 minus NG. Yeah, so that's the variety. I will tell what it is. And the curvilinear sections of this variety by a junction formula are canonical curves of genus G, right? That's not a big deal to observe. What is more interesting is that you can get in this range all the curves of genus G, the general curves of genus G, and this is Mukai's achievement. So he proved that the curvilinear sections, the moduli space of curvilinear sections of VG. So this is a this is a Grassmannian, right? So basically look at the Grassmannian of corresponding dimensions so that you get curves when intersecting with VG. And you mod this out by the automorphism group of VG. This is birationally isomorphic to MG, right? It's a very nice result, obviously. I mean, because it gives a very concrete construction of the moduli space in this range. Yeah? And maybe I should make a list here because it will play some role in our story. So V8 is the Grassmannian G26, and it's embedded in P14 via the Plücker embedding. So in this case, N8 is 8. V9 is the symplectic Grassmannian SPR 36, and it is embedded in P13. And N9 is 6. And V7 is the spinorial variety OG510 embedded in P15, and N7 is 10. Yeah. So I'm summarizing Mukai's. Mukai has a paper on each of these cases. Yeah. This is very beautiful papers. Okay. So as I said, I mean, you get very concrete structure theorems for MG for small genus, right? So what we are going to use this, and we try to bring this Mukai theory in the spin world. And essential here is the following concept, the concept of cluster. It is sort of introduced, yeah? So definition, a cluster, and the cluster is a cluster on the Mukai variety, is on VG, is a zero-dimensional scheme, subscheme, inside VG, which has to do with theta characteristic, will be of length 2G minus 2, and it is supported of length 2g minus 2 supported at g minus 1 points and with multiplicity 2 at each of these points, and such that the dimension of the linear span of this scheme is g minus 2. So what is this about? So I have the, I can write the, I can write to z, I can associate the support of z. So this is just a collection of g minus 1 points on the Mukai variety. And I have to provide a tangent direction at each of these points, right? So this zero-dimensional scheme is multiplicity 2, so it's a point and a tangent direction, right? And what I ask is that basically that for these points that if I look at the intersection for each of I, the intersection of the tangent space at pi of Vg of the Mukai variety with the span of these points, right? So lambda here is the span of these points. This is a Pg minus 2. So this, of course, I would expect to have intersection zero-dimensional, but I ask that the dimension be at least 1 for any I. So that's a cluster, right? I mean, that's more a reformulation. What I wrote here, I mean, the last line is just a reformulation of what is above. So this is a subvariety of the Hilbert scheme of zero cycles on the Mukai variety satisfying these conditions. Okay. So the clusters have, of course, now we want to get to curves. And now we will define an incidence correspondence between these zero-dimensional schemes and curves on the Mukai variety. And this is the incidence correspondence. Incidence correspondence. So the incidence correspondence is, so I look now, I call it UG minus. So I look at pairs consisting of a cluster and a curve. Yeah, so Z is a cluster and C is a curvilinear section. So it's a curve section. And then the condition is that I have this scheme theoretic inclusion, that Z is contained in C. Yeah. Okay. And then, of course, I have the moduli space of such pairs, and this can map to two in the two directions. Once in the so I have the moduli space of clusters on the Mukai variety, and then, of course, I have the moduli space of curves. But the point is, yeah, just the moduli space of curves, right, of genus G. I mean, actually, with they are already embedded in Pg minus 1, so it's the Hilbert scheme of canonical curves of genus G. And what are the fibers of this map? So when you give yourself the canonical curve, so what are the clusters that are contained in the curve? They are, of course, just the theta characteristic. They are the odd theta characteristics on the curve, right? So this is a finite map, and pi 2 minus 1 of a point is just the odd theta characteristics on C. So if you want, you remember that if you look at the moduli space of these curvilinear sections and you mod it out by the automorphism group, you got Mukai's model. If you lift yourself at this cluster level, so of course here the automorphism group of Vg still acts. I mean, the automorphism group acts at all levels. You take the quotient of Ug minus of the incidence of the cluster correspondence by the automorphism of Vg, you get this is the spin Mukai model. So Ug minus modded out by the automorphism group of Vg is birationally isomorphic to Sg minus. And this is exactly, so this is the sort of, if you wish, the Mukai model of the spin moduli space. Yeah? So let's try to make some money out of it, right? I mean, so far we have not made much progress because we just introduced some object, but this variety looks still mysterious. But anyway, this is the spin model that comes out of the Mukai construction. So we would like to determine what this variety is. When is it unirational to actually describe its structure? So now I will sort of, let me proceed. So I would like to look now at nodal curves having containing a given cluster, right? So, so look at, let's consider first of all, so let's delta, gamma rather, in VG be a delta nodal curve section of the Mukai variety, yeah? And let's assume that Z is a cluster. So this is a cluster that is contained in gamma, right? So then I have something like this. Yeah, so this is gamma. And I would like to impose a condition, namely that the singular locus of gamma is contained in the support of Z. Okay. So I have here the nodes. I said delta nodal. So here are the nodes, P1 up to P delta. And the cluster has, of course, further points. I mean, G minus 1 further points, right? So I have here further points, and these are P delta plus 1 all the way up to PG minus 1. Yeah? And then, of course, I can normalize this curve. And then I get the normalization. And this will be a curve of genus, in general, G minus delta. And then I have the inverse images of the nodes, x1, y1, x delta, y delta. Right? So these are the inverse images of the nodes. And, of course, the points, the other points. P delta plus 1, PG minus 1. So, what's the point of doing this? If you now pull back the canonical class, the dualizing sheaf of gamma under the normalization map, you will get that this is actually equal to the canonical bundle of n plus the sum of the divisors that go to the node. And what happens to the cluster? So the cluster consists of these G minus 1 points together with the tangent directions. Well, of course, the delta points will be absorbed in this divisor. But because of this formula, the remaining points, twice the remaining points, will be the canonical class of the normalization. So a cluster on this nodal curve is in fact a theta characteristic. So this yellow stuff here on the normalization is an odd theta characteristic on n. And that's the point of considering this. So this is simply an odd theta characteristic on the smooth curve on n. Yeah? Okay. No, it is contained. Okay. So what I'm saying is, if you have a cluster, right, which satisfies this condition, right? So when you pull back, so the divisor cut out by the cluster is a canonical divisor on n, which has multiplicity 2 at each of the points, right? When I pull back to the normalization, what happens to this divisor of degree 2G minus 2? First of all, this part is absorbed here. And then there is twice, 2 times P delta plus 1 plus 2 PG minus 1. And because of this formula, this is just a theta characteristic on the curve on the normalization. Yeah? Okay, so anyway, that's what I just, to summarize, a cluster on the delta nodal curve is essentially just a theta characteristic on the normalization. Okay, so then I set up the following thing, the following correspondence. So I have here PG delta. This is the moduli space of triples this time, C, lambda, and Z. Yeah? So Z is cluster. C in VG is just a random curve. Lambda in VG is a delta nodal curve. And of course, I have to impose the incidence. So first of all, that Z is contained in C as a scheme, and lambda is contained, Z is contained also in gamma, as a scheme, and this condition that the singular locus of the nodes of gamma are among the points in the support. Yeah? So this is a the moduli space of these triples. And then, of course, I can consider two projections. First of all, I can't forget the information about the nodal curve. So I can look at the moduli space of pair C, Z, and then I'm exactly, well, up to changing the factors, I'm sorry, I'm just in the moduli space UG minus that I described before. And on the other hand, I can look at the moduli space of pairs gamma, Z. Okay. And I have here two projections which I call alpha and beta. So I will be finished in 5 minutes. The automorphism group of the Mukai variety acts everywhere. Yeah? And we take the quotients. And the question is, what is this thing? I just said, right? This is just curves of genus G minus delta together with delta pairs of points and with a theta characteristic. Yeah? So the quotient of this moduli space by the automorphism group of VG is what we call VG delta minus. So this is, it's a very simple moduli space. It's just SG minus delta times 2 delta, and this is divided by the, well, this is not really GIT quotient, Z2 to the delta. So what is this? This is curves of genus G minus delta plus delta pairs of points. Pairs of points. Sorry, and there's a theta characteristic, an odd theta characteristic here, right? Plus an odd theta. That's exactly the stuff I have here. So I reduce the genus of the problem in this way. That's the whole point. And I'm going to get down to genus 1, in fact, right? So on this side here, so now I can copy this diagram when I have taken quotients by the automorphism of the Mukai variety. Yeah? And then I have here PG delta minus. This is just the quotient. Here I have alpha, and this is the model of SG minus. And here I have this thing BG delta minus. Yeah, so if you want, this is the delta fold cell intersection of the boundary divisor B0 that I described at the very beginning of the talk. Anyway, this is spin curves of smaller genus. Yeah? And the point is now that beta is just a projective bundle. And, well, you fix a cluster and a delta nodal curve. You look at all the curves that contain that cluster. This is just, so I have a PG minus 2 dimensional space in P, whatever it was, N capital NG, right? So this is a projective bundle. It's a P NG minus 1 bundle, in fact. Yeah? You simply look at planes of dimension G minus 1 that contain a given G minus 2 dimensional plane in a projective space of dimension, like in the Mukai story. Yeah? So P NG, capital NG. Okay. So yeah. So this is definitely. So if you know that this is unirational, this is a projective bundle, and you can prove that this is dominant, then you have that this is unirational, right? So what are the dimensions here? So the dimension of PG delta minus is the dimension of this thing. So this is 3G minus 3 delta minus 3 plus 2 pairs, plus delta pairs of points, so plus 2 delta, and then I have to add NG minus 1. Okay? And this should preferably be bigger than the dimension of SG minus, because otherwise we have no chance of carrying this through. And if I do this correctly, the 3G minus 3 goes away. So that means that delta is less than NG minus 1. Okay. So then here's the theorem. If there exists delta between 1 and the minimum, or 0, of G minus 1 and NG minus 1, such that this variety BG delta minus is unirational, then SG minus is unirational. Okay. So That's okay. So basically, now you know when it can be unirational. And of course, what is very tempting is to take the case delta equals g minus 1, because then you have theta characteristics on odd theta characteristic on elliptic curve. That's nothing, right? Because on elliptic curve has only one odd theta characteristic, the trivial bundle. Yeah. And in fact, we can prove this for delta equals g minus 1. We can establish this, and I'm kind of out of time. And this is actually very simple. So this is b g minus 1. This is unirational. I mean, this is just the moduli space of elliptic curves and g minus 1 pairs of points. This is unirational for genus up to 10. That's very easy to prove. But of course, we do not catch the case g equals 9, unfortunately, because Mukai, the dimensions of n9 is very small compared to n8 and n7. Yeah, so there's only 6, right? And well, the inequality is not satisfied. Of course, in principle, it could be possible to try to apply this theorem for higher delta, but we sort of were already tired, and we declared victory by genus 8. Okay, and then I said that this is also a structure theorem. So very interesting is the case, for instance, when you have genus 8, and that's the last thing I want to say, because, for instance, for genus 8, I said we determine the space. So what do I mean by this? For genus 8, this map is, in fact, is an isomorphism, birational isomorphism, which means that S8 is a locally trivial fibration, P7 fibration, over the moduli space of elliptic curves with 7 pairs of points. Yeah. So this is M114 modulo Z2 to the 7th. Yeah. So this is just simply looks at elliptic curves plus 7 pairs of points. This is very simple moduli space. Yeah. So you can ask questions. Is it rational, for instance? Whatever. Yeah. So okay. Thank you very much.
Are there any questions?
Yeah.
I'm not wrong, you have a conjecture on the slope of the big cone in the case of the usual moduli space asymptotically with G.
Yeah.
Do you have something for the spin curves case on the slope of that cone?
But so the problem is that it's not a two-dimensional it's not a two-dimensional phenomenon, so you cannot really speak about the slope, because there are two boundary divisors. I mean, there are two boundary divisors that, so in MG you get this numerical information, the slope, by ignoring one, by taking into account only the delta 0 invariant of the. So here, of course, you would have to treat alpha 0 and beta 0 on equal footing. And I don't know. So there is no concept of slope here. I mean, you are in a three-dimensional, cone, so to say, and then there is not just slope there. But we haven't, yeah.
Because I mean, in order to prove something of general type, you computed some kind of a slope.
Right, but we sort of brought it down to the question on MG, in fact. Yeah. So actually, so yeah, we brought it down to, in fact, what we showed is that the statement that S12 was a general type is equivalent to the failure of the Harris-Morrison conjecture on M12. Yeah, that was, and then actually we provided two counterexamples in the end, and I discussed one of them. Yeah.
Now, in the first part of the talk, you found an effective divisor, and then like you compare it with the canonical divisor.
Yes.
And then you concluded that.
Right. So I did this sort of fast. Yes.
This general type. I was just wondering what kind of theorem you were using to conclude that something is general type.
So I was using. Okay. First of all, from what I said, it follows that the canonical divisor is big. I mean, it's something ample. Okay. I'm using first of all Mumford's theorem that the Hodge class is big. And then I prove that it's lambda, which is big plus effective. So big plus effective is still ample plus effective, so it's big. And then, without mentioning, I used an important theorem of Katharina Ludwig, which says that the singularities of the spin moduli space do not impose adjunction conditions. And then, so basically, the Ithaka dimension of the moduli space is equal to the Kodaira dimension of the moduli space. The Kodaira dimension, normally speaking, is defined on the, the Ithaka dimension of the canonical system is equal to the Kodaira dimension. So I kind of use this. I went very fast through this, but all these things have to be used. Yeah.